Okay, and there is another method to calculate the electric current, which is called the potential method, but it is in fact the same as a loop rule. Okay, there's nothing new, and it's written here just because many textbooks deal with it, so I'm not going to read it, so please read it by yourself. But there's another thing we have to discuss, which is more important, and it is about the grounding a circuit. So in electric circuits, you will sometimes see symbols like this or like that, and these are groundings. So what is a grounding? The grounding is something like this. You know, when we deal with a circuit, typically only the potential difference is important, and we don't really care about the absolute value of the potential. But sometimes it will be still convenient to have an absolute value of the potential. Then in order to do that, you have to define the reference point or the 0 point. Or in other words, you have to define where in your circuit will be 0 in electric potential, right? So the grounding is the process providing a reference as a 0 potential. So to put it simply, in this circuit, here the electric potential will be 0, and then by calculating the potential difference, you can tell the absolute value of the potential in any part of the circuit. And actually these two circuits are the same, but now on the upper figure, the grounding is given here, so it'll be 0 here, but on the bottom figure, the grounding has moved, so the potential will be 0 here. So potential difference will be the same between these two figures, but the absolute values will be different because the positions of the grounding are different. Okay, so as an example, let's try to calculate the electric potential at A and B in this case. And here, even before trying any calculation, you can immediately tell the electric potential at B, which is 0, because it is directly connected to the grounding, which is 0. Okay, and then how about electric potential at A? So let's try to quickly calculate it. So here we have two resistors. So the total resistance is actually 6 ohm, and then the electric potential supplied is 12 volts. So by using Ohm's law, we know that the current is actually 2 ohm, and then the direction of I'm sorry, current is 2 amperes. Okay. And then the direction of the current will be going this way, and then starting from the 0 potential, if the current of 2 ampere is going through the resistor of 4 ohm, then V equals IR, so therefore the potential at this location will be minus 8 volt, and potential here of course has to be same as potential here. So at A, potential will be minus 8 volt. Okay, and then how about in the upper figure? Now the electric potential is 0 here, so therefore it's 0 at A, but then at B, how is it? The potential difference will still be the same, so therefore now at B in this figure, electric potential will be plus 8 volt. Okay, and then in real life, how do we actually make a grounding to a circuit? This figure shows you how to do that. So this is one of the examples, but here we are actually using a wire which is connected to the metallic post, which is put into the ground. So here really the charges will go into the ground. So this is where the name grounding came from. Okay, and then in this slide we will study the case of many resistors in a single circuit. So we will try to figure out what will be the total resistance when there are many resistors together. And as a first example, as shown in the right side here, we have 3 resistors R1, R2, R3 connected one after another and finally they are connected to this EMF device. And then take a notice that they are forming a single loop. So the connection in this type is called the connection in series. And then what you have to realize in this case is that the amount of current will be constant everywhere in the circuit because there is no branching out of the wires. There is only one way for the current to go. So let's call this current I, and you can see that is also I here, because the amount has to be the same, and this same current I will also go through this EMF device, okay? And then we already assumed that the current is flowing in this direction, which is the counterclockwise. Which is clockwise. So, and this choice is natural because we have the battery or the EMF device oriented in this direction, okay? So, in this case, it's a loop. So let's try to use the loop rule or the voltage law. Try to remember that. What did it say? What do you remember about the voltage law? So what the voltage law says is that when you go around the loop and come back to the same place, and when you do that, if you make a summation of all the voltage change or potential change, then finally their total summation will become 0. Okay, that's what the voltage law said. So let's apply that. So starting from the point A, and let's go around the circuit following the direction of the current. So the first thing you come across is this EMF device, and you are going through this device from the negative to the positive terminal. In this case, the voltage change will be plus VEMF, okay? And then next you are going through R1 along the same direction as the current. So we learned that in this case we have to do minus IR1, and then we are also going through R2, so it's minus IR2, and then also through R3, so it's minus IR3, and finally combining them all, we get 0 when we come back to this point A, right? Okay, and then as I said, what we really want here is understanding or figuring out the total resistance, which is the result of these three resistors connected to each other. So let's try to draw a similar circuit like this with this EMF device, but with single resistor. So let's call this single resistor REQ, meaning it is an equivalent resistor, which is the same as the combination of the three resistors, okay? So in this circuit, we have only one resistor. So let's try to apply the loop rule again. Then simply it'll be plus VEMF minus IREQ. So try to understand that the amount of current is the same between these two circuits, right? Because it's actually we are assuming the same circuit and only try to look at in a little bit different way. So, and then also we didn't do anything to the VEMF, so VEMF is the same between the two circuits. So here, using these two equations, you can finally figure out that this REQ is in fact equal to R1 plus R2 plus R3, meaning that when the resistors are connected in series, their equivalent resistance is a simple summation between all the resistors, okay? So if you, here we had only 3 resistors, but if you have like 10 resistors or 100 resistors, it doesn't matter how many you have. If all of them are connected in series, then their equivalent resistance will simply be the linear summation of all the resistors. Okay, and then let's try to think about a different type of connection, which is the connection in parallel. And here what we mean by the connection in parallel is just like here. So now the resistors are not forming a single loop, but they are connected side by side. Okay, so in this case, try to think about the junction rule or the current law, which said that when you have a node or junction,
the current coming into the node is equal to the current coming out of the node. Okay, so in this case, again, let's say the original current was I, and then it's branching out to 3 different routes, so which are going through R1, R2, R3 respectively. So let's call the current I1, I2, I3 respectively, which may be different from each other, but what we know is that now I is actually equal to I1 plus I2 plus I3. Okay, that's how the current rule is applied. And then here, instead of the current, there is a different quantity which are actually equal between different registers. And can you figure out what kind of quantity will be all equal among 3 registers? That will be the potential difference, because each register in this case are actually directly connected to this EMF device. So the potential difference across R1 will be equal to VEMF, and potential difference across R2 will also be VEMF, and likewise the same goes for R3. Okay, so for each current, for example I1, it is equal to VEMF divided by R1, and also I2 will be similarly VEMF divided by R2. So you can write the equation in this case. Okay, so it's not difficult, right? And here again the same way. Now we want to think about the equivalent registers for these 3 registers connected in parallel. And then since for the equivalent register we have only one, we have to think about only one, so we can actually use the same figure as above. So in this case, let's go back to the figure we had, and here we already know that the amount of current in this case actually again equal to VEMF divided by Req. Okay, and then similarly as we had done, these 2 equations, try to compare them, and our job is figuring out what is Req in this case. And then you can now figure out that the relationship between Req and all the registers R1, R2, R3 can be written in this fashion. Okay, so it looks a little bit similar in that all the registers must be added, but interestingly, you are not directly adding the resistance themselves, but we first have to take the inverse of each resistance and then make a summation, and what you get is again the inverse of the equivalent resistance. And so, yeah, and then when you have like 10 or 100 resistors connected in parallel, again using this sigma symbol, you can write it this way. Okay, so in this case, try to remember that if you have the resistors connected in series, you will simply add them together to get the equivalent or total resistance. But in contrast, when you have resistors connected in parallel, then you will first take the inverse of the resistance and then make a summation. Then what you will get is the inverse of the equivalent resistance. Okay.